So hello everyone, and first of all, I'd like to thank the organizers for organizing this very nice conference and workshop and giving me opportunity to talk about some beyond the standard model scenarios in the core collapse supernovae. So because George already very nicely described what role neutrinos play in the core collapse supernovae and what is exactly the explosion mechanism, I will just try to briefly stress a few points. So core collapse supernovae are one of the most efficient neutrino producers in our universe. They are deaths of rather massive stars. And here you can see this onion shell-like structure that forms towards the end of the massive star life. So once this very massive core inside grows to a substantial size, then its gravitational pull will at some point overcome the electron degeneracy and the thermal pressure, and this core will start collapsing. Because of this collapse, we can then launch a shockwave, and we can observe later the supernova explosion evolving into the neutron star. But in some cases, we can also see that the collapse process leads directly to a formation of a black hole. So in both of those processes, we see a large amount of neutrinos being emitted. These neutrinos carry pieces of information about the deep interior structure of this collapsing star. And in case of the direct collapse to a black hole, these neutrinos might be the only messengers we can detect. Then by detection of these neutrinos, we can actually probe environments that are not really accessible on the Earth. And especially if we see neutrinos from the nearby supernovae, not only in the, what I would say, more ordinary detectors like IceCube, Dune, or Super K, which focus more on the electron flavors, but also in the direct dark matter detectors, we would have very nice multi-channel detection that will allow us to learn something about more of the astrophysical unknowns, like the explosion mechanism or maybe the nucleosynthesis of heavy elements, but also compact object formation. But we can also learn something about more of the particle physics unknowns. And as George was saying, the neutrino favor evolution in the dense environments. But maybe we can get some hints about the non-standard physics. And if not hints, if we are not that lucky, maybe we can improve our constraints. So during this case here, we saw a very nice picture of the neutrinos in the standard model, where in this model we have neutrinos being chargeless and massless. However, from the observation of the neutrino oscillation, we know that these particles actually have mass and can oscillate between each other. So I think now we know to a good extent, like for me from the supernova side, most of these parameters, but we still don't know how active neutrinos get masses. And also another question that we can ask about the standard model is we don't know what is dark matter. So by then introducing some models of the sterile neutrinos, massive neutrinos, we can sometimes even simultaneously solve these two problems. And we've seen also talks about that. In my talk, I will focus on these 3 different mass ranges for sterile neutrinos. And basically, by choosing different ranges, we try to solve problems associated either with terrestrial observations or, as I said, also by solving neutrino mass or leptogenesis. So in case of the Amyv mass steroids or sub-GeV, this could be motivated by possible explanation of leptogenesis, but also it is motivated because we can test it in the terrestrial experiments. And in addition, there will be impact on the core collapse supernovae. For the KeV mass steroids, they are so-called natural dark matter candidates, as we heard yesterday from Kavli. In addition, they are testable in Catherine/Tristan or Hunter experiments, and they also are expected to have some impact on the core collapse supernovae. And finally, moving down in mass, we can look at also the EV mass steriles, which then on the other hand are motivated by some reactor and gallium anomalies, as well as the mini-boon, LSND, and microboon anomalies. But they also should have impact on the core collapse supernovae. So I will start with the Amyv mass neutrinos in the core collapse supernovae. And here you can see a plot which shows the parameter space that is showing available and excluded ranges of the mass and then the mixing angle for sterile neutrinos that are assumed coupled on the tau sector. And I chose that because the constraints on the electron and mu coupling are much more stringent, so there's not really a lot of parameter space that can be explored in the core collapse. So here we can divide those constraints for constraints from the terrestrial experiments, like pion and meson decays, but also we have the Big Bang nucleosynthesis constraint, which is in case of the standard cosmology, we want those heavy particles to decay before the Big Bang nucleosynthesis commences. So now moving to the core collapse and what those particles can do inside there. So because we are dealing with very hot and dense cores that is basically full of neutrinos, then that are very energetic, then we can have annihilation channels that lead to the production of this heavy sterile particles. And basically, this is the dominating channels because besides being hot and dense, the core is also degenerate, so we cannot really do much with these particles. But for tau neutrinos, we have a lot of them, and also they are not degenerate. So on this left-hand side plot, you can see the luminosity of sterile neutrinos being produced by those interactions with this dashed line, and then the tau neutrino luminosity as a solid line for certain value of the mass and mixing. So here it is still below this tau neutrino luminosity, and it was calculated assuming that there is no feedback on the star. And if you want to just look at some snapshots, then we can see the spectra basically looking like this. But here the mass of the particle is heavier, so that this side, the authors assume that is still trapped by the gravitational potential, the heavy core. So now, because we can have numerous production of these particles inside the core, we can also ask a question about limits, or maybe better, like the parameter ranges which would affect the core collapse supernovae. So here we can have two types of effects. I mean, two types of effects and one observable maybe feature. So we can have an additional cooling channel that will take away the energy from the core and basically could possibly shorten the neutrino emission. Then we can also have the heating mechanism, because these particles can decay still being within the envelope of the star, so they can deposit some energy and re-energize the shock. And finally, in the decays of these particles, we can produce very energetic neutrinos. And if these neutrinos are able to escape the star, so the decays happen rather far away from the core, then we can possibly observe not only the normal spectrum of neutrinos from supernovae, but also some suppressed highly energetic part. So here you can see the potential limits on the mixing angle and mass from assuming the energy loss constraint, and this is calculation without the feedback. So it affects some of the region of the parameter space that we see here. But if we move now to this work, where the authors actually try to include these massive particles inside the 1D supernova simulation, the results might be analyzed in kind of different way. So in standard case, the simulation didn't lead to explosion. And by including the production and decay of these particles, they try to see if then the simulation would end up in the explosion. So here, all those diamonds that are colored means that the simulation ended up in the explosion. So here, these 4 didn't. And we can see what was the explosion energy here. But in this region, they assume that the constraints from BBN are affecting already the mass and mixing. In the gray region, they say that they can see some effect, but we cannot really draw very robust conclusion because we can be just some uncertainty in the modeling of the simulation. And then in this region, which is called too energetic, it means that the energy of the explosion was basically more suitable for hypernovae and supernovae. So I wouldn't exclude this region neither. Okay, so now I will switch gears and go to a smaller mass, so Kavli masses. So here we can also look at the parameter space, which shows some favorable regions, but also constraints on the masses and the mixing angles. And the favorable regions come from the explanation of pulsar-kicks, maybe by sterile neutrinos, and also the observation of 3.5 Kavli line that we heard also about yesterday. And the constraints come from the Tremie compound, so the phase space constraint. We can have the radiative decays of sterile neutrinos, as Hevok was also talking about yesterday, and Graciela. We can have dark matter overproduction, which is here, but this is the dark matter overproduction assuming standard Dodelson and Windroff, which can change if we add non-standard physics or non-standard cosmology. And finally, we can also have the supernova energy bounds. In that case, the impact of the Kavli sterile neutrinos has been studied for quite some time in the supernovae. And this studies show that we can potentially have the suppression of the explosion if we take away too much of the energy by emission of sterile neutrinos, or maybe even enhancement if those neutrinos now not decay, but actually reconvert by the oscillation to the active states. And in addition, it has been shown that the production and propagation of those sterile neutrinos can lead to development of neutrino and also other particle asymmetries. So if we just do the calculations without any assumption of feedback on the supernova medium, we can see that these simulations, these calculations can actually exclude some of the regions that are not yet excluded. So Irene, Mengru, and I try to check if that changes or not if we assume some feedback. In our models, then, we use the 1D supernova neutrino background from the Garten group as our background. And then in case of the electron sterile mixing, we also introduce the feedback on the temperature. But basically in the core, you can produce Kavli sterile neutrinos either by the MSW resonance, so the enhancement of the conversion probabilities due to the effective potentials spared by those particles from other standard model particles. Or we can also have collisional decoherence. So in case the neutrino, the neutrino that is produced inside the star scatters on mostly neutrons and protons, then because it's actually a mixture, once the scattering occurs, the wave function can collapse to active or sterile state. So in that case, then the production scales as the rate of scattering and also effective mixing angle in matter. In the case of tau sterile mixing, we expect only one resonance, but for the electron sterile mixing, we can have multiple resonances because then electron neutrinos can have charge current interactions with electrons. So here are just some equations. In case of the collisional production, we have the conversion probability that depends not only on the mixing parameters and effective potential, but it also depends on the damping rate. So in case the collisions are too frequent, the conversion probability will be suppressed. And for the MSW production, because we have very small mixing angles, we can approximate it by the Landau-Zener formula, where the probability of conversion basically depends on the adiabaticity, which is the ratio of the resonance wave to the oscillation length. So if it's large, then we produce a lot of sterile neutrinos. So here on the next slide, you can see the effective potentials and then the resonance energies and chemical potentials of neutrinos in case of the sterile electron mixing on the top panel and then sterile tau on the bottom one. So all the lines here that are plotted as dashed lines are just at the start of the simulations where there is no feedback on the supernova medium from the production and propagation of the sterile particles. But the solid lines show then the change that occurred during simulations that run for 1 second. So here we can first see that since all the effective potential in that case are always negative, we only have the MSW resonances for antineutrinos. In addition, because the production of the sterile particles from the electron neutrinos or tau antineutrinos leads to growth of the chemical potentials and effective potentials, then the further production is suppressed because we basically suppress the Fermi-Dirac distribution of antineutrinos. So now I will just briefly sketch the how we did it for the tau neutrino mixing. So we assume that in standard case there is no asymmetry, the mu tau is 0. But in the case of active sterile neutrinos, we know that the conversion probabilities are different. So it would lead to the development of the tau neutrinos asymmetry, which then can be translated to the chemical potential, which changes and also changes the effective potential. So basically we have this feedback coming from sterile neutrino production on the further sterile neutrino production. Here you can see how that changes the Y nu tau, so tau neutrino fraction, chemical potential for tau neutrinos, and effective potential. So starting from light to dark color, we go in time, and we see that actually the chemical potential grows as well as the effective potential. And then the Y nu tau also grows, but never actually reaches the saturation value, which would be if the effective potential would go to 0. So now finally to the limits or region of the parameter space that would be affected by those particles. So because we, in the standard case, emit most of the binding energy by the active neutrinos, and then if we have the conversions between active and sterile, some of that energy can be converted to sterile neutrino. Then we can put a bound saying that, okay, if all of that energy is converted to sterile neutrinos, then we can possibly rule out this region of the parameter space. But we saw that as we included the feedback coming from the sterile neutrino production and propagation on the chemical potential and effective potential, this region of the parameter space actually shrunk significantly. So the same story was for sterile electron neutrino mixing, which was a bit more complicated because now we can have discharge current reactions, which drive the beta equilibrium, as George was pointing out. So now when we deplete this electron neutrinos for antineutrinos, we have to basically resimulate what is our new equilibrium state. And we did that by simultaneously solving this 5 equations. And so now we not only have the feedback on the chemical potential of electron neutrinos, but also electrons, protons, and neutrons, but as well the temperature and entropy of the star. So in that case, we can again see how the now the sterile neutrino number and then the chemical potentials of all these particles and fractions changes. So here, maybe we can focus just on this middle panel when we see the change in the chemical potentials. So basically, because we started with some chemical potential for electron neutrinos, we can then have the increase or decrease of that chemical potential depending what is the most efficient mechanism, which then depends on what is actually the mass of the sterile neutrino. And again, we can then compare what are the bounds or regions of the parameter space that would affect supernovae. And here we see the same story, that in case when we don't have the feedback, we can exclude some region of the parameter space not appropriate. Once we have it, then this region basically shrinks, and for even the electron sterile moves away from this parameter space. So the conclusion from this part is that the feedback in our simulations already greatly affects the results, but this is not yet fully consistent picture because we didn't include it in the supernova simulation. So now I will move on to the sterile neutrinos with EV masses in the corpora of supernovae. And again, we can look at some limits and hints, which were also discussed during this week. So here is the plot for the mixing with the electron flavor. So the hints that we have or we think we have can be from the reactor experiments, the gallium anomaly, and microboom that is, as Ornella was saying, not yet released by the microboom collaboration, but there are some papers I know by Joachim and Mateusz and also Peter Denton. But also we have some limits, especially from the solar neutrinos, but also reactor experiments, then as well Catherine experiment and Prospect. But we also have very strong limits from cosmology. However, this can be alleviated depending on if we have standard cosmology or if the sterile neutrinos also talk to other particles or not. So now coming back to the core collapse supernova picture, we have this 6 stages of the collapse. So for the EV neutrinos, people usually focus on the last stage, so neutrino cooling after we already had the explosion, and then neutrino different wind. So I think Amol and also Gay will talk more extensively about the nucleosynthesis. So I just sketched the idea because we have these reactions, charge current reactions again, happening outside of the core. And basically they are now going in this direction because neutrinos are decoupled, so they are energetic, but the medium cools down, so it cannot emit again. It cannot go in that direction. So because of that, we can have the so-called neutrino-driven wind if these neutrinos deposit enough energy to push the material out. And as already George was also saying, and we hear more in these 2 talks, the nucleosynthesis, the R process especially, I think nucleosynthesis is extremely sensitive to the YE, so the fraction of electrons, that this in turn is actually defined by the ratios of these reactions, and basically it freezes out when they freeze out. So now what's going to happen if we introduce the sterile neutrinos to that picture? So here we can again see the region of the star, and YE is red, and then that's basically some measure of the potential that neutrinos are that they're feeling. And now for the EV steroids, we are looking at the outer region of the star because the delta n squared is smaller. So here we can also have the potential that has this double shape, but now we can have as well conversions enhanced in the electron neutrinos and also anti-neutrinos when this potential crosses zero. The most of the result depends also like how adiabatic is this conversion, and it will be more adiabatic for higher neutrino masses and lower energies. For smaller neutrino masses, it can be less adiabatic, but basically it leads to the deflection of YE, and that effect can lower the depletion of electron neutrinos, and that can lower the YE. So here, for example, you can see the evolution of the already frozen YE as a function of post-bounce time. In the case of simulations with this, they just look at this black line. When we have just active neutrinos oscillating, but that didn't introduce a lot of change because they are already close in the cooling phase, so they have similar distributions. But when the sterile neutrinos were introduced, we could see that Y would actually change significantly, and especially at a later time, it was decreasing, which would be favorable for the R processes. Then also newer study was done by Young and also I think Gru and Yon Chen, and they again looked at the evolution of the YE as a function of time and radius, but now as well by modeling the wind themselves, like taking into account what the sterile neutrino conversions would do to that part. And they also seen a similar effect, that introduction of the sterile neutrinos lowers the OE. So if we now move from the blue line to both of this black and green, we can see the reduction. And here you can see how the survival probabilities for neutrinos and anti-neutrinos look like as a function of radius for the different post-bound times for different masses of sterile neutrinos. So here, the red one is the least massive neutrino because the conversion is not very adiabatic, and then the second happens far away. And as we move down, we move up in mass. So this is like 1.7 EV, and this one was, I think, 0.4. So from both of these effects, we can then translate it to the what happens to the nucleosynthesis, especially for the R processes. So they saw that for early times, they can actually increase the production of elements up to like almost around, I think, 45 atomic number. And yes, but again, here as well, more studies are needed because they assumed that neutrinos only mix. There are only two flavors, sterile and electron, but neutrinos also mix with the X flavor, and that was not included. And also the neutrino evolution was approximated by the single angle approximation. So we know that there is still work to be done. Okay, so I think this brings me to my conclusions. So if we look at the sterile neutrinos with masses between EV to Amyv scale, we saw that they can have a major impact on the supernova physics or also the nucleosynthesis. They can lead to the growth of asymmetries, can affect the explosion mechanism, and possibly might even lead to detectable features. However, we still don't yet have the full picture because we need to improve our modeling of the sources, neutrino evolution, and also modeling of the BSM physics inside the supernova, not the model building. So I think we have some exciting things ahead of us, and we can do some more work to improve what we see now. Thank you.
Thanks for the great talk. So much covered. In terms of the feedback versus no feedback models for energy loss at the KeV scale steriles, you had kind of like the results at the end, but I think you also had them at the beginning with all the other constraints. Is that right?
Yes, those were without the feedback.
Those were what? Sorry.
Those are without the feedback.
Okay. So, but so you don't have a version of this with the other.
No, I also have it, sorry, here.
Ah. Okay. I missed this one. Thank you. Okay.
So if you want to make the R process from supernovae through sterile neutrinos, and a really good R process, not just an okay R process. So you want your YE to be really low, and you're allowed to build, add any number of sterile neutrinos. How would you do it?
Yeah, I think I would want to deplete basically also the X flavor, because then I wouldn't have the oscillation between the electron and X. So that maybe could possibly deplete the Y even more, but I'm not sure if that would be enough.
Other. Yeah, one question. So in the case of the once you have a sterile neutrino, you are interested just to include the oscillation. At the masses that you are considering, I guess the coherent length also can affect the oscillation, because typically for a standard oscillation, for a standard masses are very long, but if you include the mass of the sterile neutrino it's very short actually. So did you take that into account, or can that play a role?
So for the EV, I think it can play a role, and probably is. For the KV, I'm not 100% sure, because everything happens already inside the proton-neutron star. So basically neutrinos cannot yet free stream.
Okay.
So yeah, but there could be some effects, I guess, if there is some asymmetry, because then your neutrinos would basically travel different distances that could lead to a different conversion, the conversion at different radii, depending on at which angle you are.
Okay, thank you.
Other questions or comments? Is there any possibility to detect any of those effects with the next generation of neutrino experiments? Do you have any robust observable for us?
I'm not sure if it's very robust, but especially for the Amyv neutrinos. So if I produce them, then they can decay and they can produce high energy neutrinos. High energy in the sense of Amyv scale, not high energy IceCube. So if we have a supernova kind of close by and we are lucky to see this bump at higher energies, this could mean that we have some MEV scale.
That means looking at higher energies than the one that we expect to have there. This is for which flavor?
So this is, I think it was for Nui bar, because they show the numbers. So basically it's like 5 to 10% of the total number of events in I think Super Kamiokande. And here they assume also that neutrinos are just undergoing later on standard MSW.
Is this in any paper?
Yes,
we
yes,
can find that.
Yes, this is in, sorry, it was from, in this paper.
Okay, perfect. Thank you.
Other questions or comments? Okay. If no, let's thank Anna again.
Thank you.
And we can take a break. So wait, when would we return from the break? 11. So 40 minutes break.